Professor Mike DeWeese from the University of California, Berkeley, who is a professor of both physics and neuroscience, like this was a movie. And his research interests include theoretical non-equilibrium statistical mechanics, information theory, machine learning, and both theoretical and experimental systems neuroscience. And today we're going to hear about neural tangent kernel eigenvalues accurately predicting generalization ability.
Yeah, hey, thanks, Steve. A lot of fun to give a talk at Fenrir about this stuff. I'm really excited about this work. This is, and who did the work? It was Jamie Simon and Maddie Dickens, two graduate students in my group with strong physics backgrounds who have gotten interested in neural networks, but they're really focusing not on the biology, they're really focusing on artificial neural networks and machine learning problems. So what I'll talk about today is a theory that they cooked up. Jamie is the lead on this, who came up with the original concept and got really the point of the spear on it. But they both contributed substantially to the results. But the question we have is, how should you design from first principles, or how would you even go about designing? I mean, this is really first steps here. How do you go about using first principles to design a neural network that's going to do what you want it to do and do it with the least amount of training data? That's the basic question. So I'm going to give a little intro here. Say, all right, so question of generalization. What do I mean by generalization? So if somebody gives me a network and some target function, I'm going to train this network, and it's going to be a deep neural net, right? This network. That's what I mean by a network. I'll draw a picture of what I mean by that in a second. And I have a particular goal in mind. I want it to perform some input-output target function that I want it to do, and I want this to be learnable efficiently, right? And so in parentheses here, I say, well, there's lots of things you might think I mean by that. One has to do with, you might think I'm talking about expressivity, like how do I design a network that can represent any possible input-output relationship? That's a question that's long been studied, and there's a lot known. It turns out that pretty much all the networks we might consider are going to have so much expressivity. The issue isn't whether or not they could in principle represent some input-output relationship. The question is, how do you design the network so that it can learn quickly? And by quickly, I mean with the fewest number of training examples to generalize properly to non-training examples to do the thing you want, to have the right function. All right, so here's my neural network. Information's flowing from left to right. Each of these nodes or neurons or units or whatever you want to call them, these are circles here. These things have activity, which is just means they have some current value given whatever the input was. Over here on the left is my input. This is my input layer. This is in layers, and it's a feed-forward network. It's going left to right as I've drawn it on the page here. And there's 1, 2, 3, 4, 5 total layers going on in this particular cartoon network. There's 3 hidden layers. Hidden just means not the input layer and not the output layer. I think most people know what this is, but just we're on the same page. And so the way this thing works is I give some particular values to the input layer. In this case, there's only 2 units at the input layer. And then what happens is it gets processed by the network. I have parameters in my network. I have gazillions of them, right? Every connection in this fully connected feed-forward network, every connection from this guy to this guy, and then this guy to this guy, or this guy to this guy. In each of those cases, each of these gray lines has associated with it some weight. I multiply that by the activity. So this has activity, whatever it is, 1, or well, let's make it a more interesting number, 2. And then maybe the weight from here to here, but the theta is equal to 3. Okay, 2 times 3 is 6. You get the idea. You get 6, and then you get some other activity times another weight. You sum those guys together. I think I've got a little cartoon of what that looks like. You're just going to sum. In this case, you only have 2 possible guys to sum because there's only 2 neurons in the previous layer. And as you go to this guy, it's okay, you sum those guys up, the product of the activity here and the weight, activity weight, okay, fine. And then you put it through this thing A. What is A? That is my activation function. That's the nonlinearity that makes the network interesting. So if all these things were linear, it wouldn't matter how many layers you got, it's just a linear network. Linear networks have some interesting properties, but in general, we're interested in nonlinear networks, right? And what kind of nonlinearities do people use? Well, they use rectified linear or ReLU sort of nonlinearities that are equal to 0 for negative numbers, say, and then equal to the number itself for positive numbers, maybe a tanh function, right? Or it doesn't really, well, I shouldn't say it doesn't matter. It does matter, but all those things and many other choices are valid choices. The question I want to ask when I say what network should I use is, if I have just for today, we'll talk about fully connected networks like this one, where it's a feed forward, but every node in one layer talks to every node in the subsequent layer. So that's when we make it fully connected. And then we're going to put the same nonlinearity, say, in every one of these gray lines. Which nonlinearity should we use? And how many layers do I want? How many layers do I want? Those are the kind of questions. How should I design it? And so people now do that empirically. They do it by trial and error, essentially, is the main way. That's the cutting edge approach people have used for the most part to figure out how to design their network. So I'll show you a theory that will actually allow us in principle to do that for really complex problems. I'll show you that it works really well for toy problems. The width of the network, when I talk about the width later on, we're going to take the infinite width limit. So it's like a pretty physicsy thing to do, and we will do that. What I mean is how many neurons you've got or units you've got for each of the hidden layers. I'm not going to change the number of output units. In fact, we're going to stick with one, because without loss of generality, we can just talk about one output layer. Sorry, one output unit. If you have other units, the theory would apply to each one individually. So I'll just talk about one output unit, but it doesn't matter, you can have more. And then here's my input. It has 2 in this case. For this problem, when I take the infinite width limit, the number of those green circles explodes to infinity, but the blue ones and the green ones, it's going to stay at 1 and 2 respectively. All right, great. So this is what I just said a few minutes ago. How do people currently figure out what network to use? They just know a lot because they've tried a bunch of things. There are papers that are cited huge numbers, like hundreds and hundreds or 1,000 times, where essentially what they do is take a laundry list of nonlinearities for those activation functions we talked about and just try them all and see which one works better for solving some benchmark problems. So we're going to hopefully be able to do better than that with some pure theory. So here's our warm-up problem. So here's a toy example. Suppose my data can be drawn from the unit circle. So here's my unit circle. And every single point on this unit circle in this 2-dimensional space can be represented by 2 numbers. You know, it's x and y position. It's sine theta, cosine theta, where theta is the angle from horizontal, say. And there's a discrete number of points here. If I want to do a continuous circle with my theory, what I'll have to do is take the limit as the number of dots goes to 0. But I can do that. I'm just going to focus on the discrete case for this talk. And in our paper, we do the same thing because it just turns out the math is easier. But you can take the infinite number of points limit and then take the continuous limit, and you'll get answers for what you do when you've got a data that can be drawn from some continuous distribution. And in fact, we tested the theory on models like that, and it works. So, okay, great. So that's our input to the network. And what function are we going to learn? So I'm drawing now a whole bunch of results for what happens when you try to see what the generalization is for my neural network when I train on n points. So what am I doing? I'm showing you n specific points, okay, in this graph right here. So here, and by points I mean different values for theta along my horizontal axis. So in this particular case, I have this theta value, this guy, this guy, this guy, and then I trained my network. I went ahead and I ran the network an infinite number, or many, many times, effectively infinite number of times, by drawing with replacement from that data set of just 2 to the 2 is 4, so 4 data points. And so if I do that over and over again, eventually my network generalizes according to what you see with this sort of cyan curve. That represents the generalization of my network after many, many iterations of training, to the point where it's really converged. It's doing as well as it can. It does a perfect job at the data points. See that? Perfect job. But in between, it does whatever it does. Now, that's not what I wanted it to do. What I was hoping to learn was this function. Okay, that's my target function. That's the thing I'm training on. And you see that the data points agree with that function, but the points between the data points don't, because it didn't generalize the way that I wanted it to. And what network am I using? It's actually a 4 hidden layer network with ReLU nonlinearities for my activation functions. It's width 500, so it's not infinitely wide, but it's pretty wide. And so this is what you would get if you were to do that. If you have a greater number of points, so here we're training on more points. What's that? 16? So 16 points, and you see that you do a better job of generalizing. right? Now we're doing a better job of capturing the function. Now when we go to 2 to the 6 points, okay, now we're doing even better. We're doing a really good job of interpolating well between the points, and no surprise, right? Because you have so many more data, you do a better job. Now, if we ask, what if we're trying to learn a different function? What if this is the function, which is a wigglier? It's a higher frequency sine wave as you go around in theta, right? In this case, it turns out you do a poorer job of generalization, right? You still do a perfect job where all the data points are after you train for an infinite amount of time on your n data points, but as n increases, you have to go to a larger value for n before you start, before you do as well as you did with a smaller number of points for a different function you were trying to learn. In other words, this neural network that I'm describing down here that we're training is better at learning this function than this function, okay? Why is that? How can we predict which functions are going to be better at learning? Well, we'll get to that in a minute. I'll just show you some more things about this toy example. How do we assess what a good job we're doing as a function of the number of points? The usual way it's done is by looking at the error, in particular, the mean squared error. In fact, I don't think I said this explicitly earlier, but when I train my network, what I'm doing is I'm minimizing my mean squared error. And so that's a pretty obvious thing you want to look at to get an idea of performance. And what you see is that over time, yeah, mean squared error goes down as you increase the number of points. N, little n is the number of points you're training on, right? Out of all the possible points you might have seen and trained on. And what you see is, yeah, it goes down. And in fact, it's going down faster here than here, indicating that the network is better at learning this function than this function. There's some other weird things that are happening. I'll just mention it. I'll talk about this a little more later. But actually, if you look closely, and we saw this in previous papers that have worked on this kind of stuff, the mean squared error actually can go up sometimes with the number of training points. And that's weird. It's true, but it's weird. It's one indication that maybe there's a better way we can quantify how well we're doing it at learning a certain function. So, so that's my mean squared error. How do I represent that? Well, you know what mean squared error is. I'm writing it in a weird way as some kind of an inner product with this funny notation where f is the function that I'm trying to learn. That's the sine wave underlying these points here. And then f hat is what the network actually does. That's my approximation for the thing I'm trying to learn. What do I mean by this notation here, this inner product? What I mean by that is for all m, capital M points that I might have seen in my input. So in this problem, there are a total of how many points around that circle? I think it's 256. I think it's 2 to the 8. So m is equal to 256. For every one of the points I might have seen out in the real world as my input, right? I'm gonna sum over the product of two functions. They're both scalar functions. This gives me a number, this gives me a number, g of x and h of x. And so if you think about this again, you know what mean squared error is. So that'll just sort of tells you what I mean by this thing. So you already know what mean squared error is. If I take the function that I want to train minus the thing that the network actually gives me as its output, this is just the error, right? If I multiply it by itself, that's a square error. If I take an average across all possible points that I could have shown to the network, including points that I didn't, including points over here and over here that I didn't include in my data set, right? Then I get mean squared error, right? So that's all that is. Now, another thing I might do is ask, well, what if there's a different function? I'm calling it phi sub 5. That corresponds to the function that, as you might have guessed, has 5 cycles instead of 2 cycles or 7 cycles. It's another sine wave that I might have also tried to train but didn't. And I ask, well, how much overlap or what is my inner product here between the thing that the network learns and this other function I didn't try to learn? And what you notice is that, well, for intermediate values of the number of points I trained on, there's a big spread in what I get for this inner product. But after a while, it closes down on 0. So when you really learn the function well, you're not actually learning other functions, right? You've learned just this function or just this function, right? And after you've done it sufficiently with enough data, with a big enough data set, then it turns out that you don't learn other functions, and that's a good thing. We chose this function as orthogonal to the one we want to learn, so we don't want to have any any spillover or any contamination from other things that we're not trying to learn. So that's another way you can assess the quality or the efficiency of learning as a function of the number of data points. And now here's a third thing. And both this measure and this measure that I'm describing now, this is new to our work. So this is a new idea. And this learnability is going to be something we'll use a lot in this talk. Learnability can be represented as the ratio of two of these funny inner products. It's the inner product of the function you're trying to learn and your network's function divided by the inner product between the function you're trying to learn and itself. Okay, so it turns out learnability has lots of nice properties. I think I'll see that on the next slide. And what you can see here is that it goes up when you learn more. So if you look at larger and larger data sets, you do a better job of learning the function of interest, it goes up. And this never goes down, unlike mean squared error, which sometimes can go up as you look at more data, which is weird. Especially when you consider this isn't like you're looking at some weird choice of your data. This is averaging over all possible things you might have seen, right? It's a pretty fair assessment, but anyway, so that's one property of learnability that we like. So I should say that the idea of using the sort of some aspects of the kernel methods I'll describe in this talk was figured out by other people before us. So about a year before us, a nice paper came out that we only discovered soon before we published ours, but a really good group figured out that you can use these kernel methods to understand, to say something about generalization in neural networks, and they assessed it with mean squared error. What's new about our work is that we're using other measures and that we're able, and we have I'll show you some other things too. We have a no free lunch theorem, actually, that's more powerful than previous theorems. And we have a framework that we think is going to allow us to actually do more principled model selection for hard problems, like trying to identify cats in photographs and stuff, once it's fully realized. So, okay. So after all those big promises, let me turn to the next slide here. Oh, yes. And if you want a detailed, I'm going to show you some math as we go with the talk. But for the most part, can I hide this bar? My little Zoom bar is in the way. Oh, it chokes me up to see that. But my Zoom bar is in the way of my little reference here. But this should be our archive paper that's up now. You can look at it in the archive with these authors. It's the only paper that's got that set of authors on it. And that goes into detail for all the stuff I'm describing you. Almost everything I described today is in this preprint. So I'll give you a hint of the math here and there, but we're not going to go through every detail. And you'll thank me later. I didn't go into every detail on what's supposed to be an hour talk. Okay, so infinitely wide nets is the same thing as kernel regression. This is not new to our work. This is over the last 4 years, people have noticed this. Turns out that if you go on the infinite wide neural net limit for fully connected nets, and frankly, for other kinds of nets like convolutional nets and transformers and other kinds of things as well, you wind up with a kernel regression equation. So what do I mean? So this is just a bunch of notation and some basic ideas. Here is my network. Remember, it's got the hat on top. This is the approximation to the function I want to approximate. So capital, my funny chi x here, that's my space of possible data, possible inputs. These would be photographs of cats. The RGB values, or the gray values, every pixel as written as a vector might be what this is, right? For one of those examples, right? And then the real number output, that just says, like if you see a cat, maybe you want it to say 1, or maybe you want it to say 0. If there's no cat in the photograph. Real valued means that usually these networks that do that, they give out a real valued number between 0 and 1, and you train it so that it tends to give things closer to 1 or 0, depending on what's in the photo. So that just describes our network. That's just what the network does. Our L is just the loss. I would call it a cost function. That's how I was raised, but computer scientists often refer to this as the loss. It's just the mean squared error. It's the thing the network gives you as a function of its input x, where little x is just one example drawn from all possible inputs you might have seen. And then y is the thing you want it to say, right? This is when some human looks at the photograph and says, oh, yes, there is a cat there. We're going to call that number 1. And there's no cat there. Okay, it's a 0, right? So this is the desired output. That's the thing you actually got. You square it, that's your loss. And what do you do when you update your weights or train your weights in your network? Remember, theta are our parameters in the model. Those are the weights. What you do is you change the weight a little bit by taking a gradient of the loss with respect to your weight. You multiply eta, which is just some number. It's a learning parameter. It's just how your learning rate, how quickly do you want to do this, right? Minus sign, because you're doing gradient descent, not ascent. You're trying to minimize the loss. And then you just follow your nose. And now you can take this equation, take a derivative. In fact, it's a multi-dimensional derivative. It's a gradient, right? Because you have lots of different parameters you're changing. And you get this function. This is just backprop, it's gradient descent, right? Okay, so now we're going to linearize our description of our function, our new network after training, right? After one time step in training, responding to some new data, some new photograph that you haven't seen before here, right? Well, what does that look like? And well, you can follow your nose. We're just doing essentially a Taylor series. I think a mathematician might complain that I called it a Taylor series, but that's essentially what it is. You're just linearizing about theta equals 0, or excuse me, about theta at time step t plus 1 equaling theta at time step t, and then a little correction delta theta, right? And if you write this out, plug stuff in, you wind up with this curious object here, which I'm going to, as Steve would say, oh, this thing shows up a lot. Let's give it a name. It's used to say in grad school days. And what we're going to call it is the Neural Tangent Kernel. Very important object for our theory. What does this do for us? Once we recognize that looking at training, there's this important object, at least when we linearize, like there's correction terms here, right? Well, it turns out that if you have an infinitely wide network, and here's 4 papers here that are really seminal papers that came out in the last 4 years that made this observation, that if you have an infinitely wide network where we take that limit where the hidden layers have an infinite number of nodes, and if you do some clever stuff with your normalization, which is sort of common sense, but you got to be careful so things don't blow up. When you let something go to infinity, you want the outputs to be finite and you want things to behave. So you do the sensible normalization, which they describe in these beautiful papers. It turns out you reduce the problem of looking at a neural network. So here's our network function. You can write it in terms of this sort of kernel regression equation, where K is our neural tangent kernel that we saw back here on the last slide. It's just this thing, right? Which is just a function of gradients with respect to your parameters of the network, right? And in fact, there's 2 of them here that you're taking a dot product between them. So this big object, it's a big matrix that is in its full glory. It is the size of the input by the size of the input. So we're doing this in discrete space. So the number of input, like I know photographs of cats, there's an infinite number of photographs in, well, not really, but it's essentially infinite, right? But for our theory, we're assuming that's finite. We can take that limit when we're done and let it go to a continuous space. But we'll just keep it finite for the purpose of keeping the math simple for our talk. So this thing is just the kernel regression equation. In fact, it's the same thing as what you know from linear regression. Just plain old vanilla linear regression follows the same equation. In fact, the theory I'm going to describe to you is about kernel regression in general. So our results apply to linear regression, not just to neural networks, to deep nets. Though I won't talk about that so much. I'll talk more about how to think about it in terms of neural nets. So one way to think about this equation that helps me out is I say, well, so is there a reduction here? Is it helpful? Yeah, well, the number of inputs we've got, really, there's, this capital M is the size of my, there's a number of points around that unit circle in my toy example. It's the number of possible photographs I might show the network after training is over to see what it does. It's the space of all possible inputs. It's huge. M is huge, right? But this thing, even though it is an M by M matrix, the part that matters for training on a given data set is really just, this thing is, so what do I mean by this notation? This is a particular photograph or a particular data point at the input. This thing, cap script D, is my data set for training. This is my training set. And there's little n data points, just like we saw before in this first graphs I showed you. So this thing is a 1 by n object. This is an n by n object, and it's inverted. You have to take an inverse. In fact, that's the hard part of using this equation. You have to take a matrix inverse. And I'll say quickly right now that, one reason why you say, wow, you've reduced this to this simple equation here. Why not just do this and forget about the neural network? And the answer is, yeah, you can do that when you're in a small enough, if n is small enough that you can do this inversion easily. But it turns out that's a nasty operation. Well, not nasty, but I think it goes like n to the third power or something like that. In terms of how many steps you have to go through to invert an n by n matrix. It turns out that I think the way to think about it is that training a real neural network is in a way an efficient and well-ordered set of steps for doing an inversion of this kind of a kernel. That's one way to think about it. You're sort of doing a matrix inverse in a smart, efficient way, where you look at the most important parts first and then the less important parts later. And you can do it as long as you want and stop whenever you want, and you got a pretty good approximation to the inverse. And then this is just the function we care about, function we're trying to learn, and it's a function of our data set. So it's an n by 1 object. Anyway, so these things are smaller than this is. One thing I haven't told you explicitly, let's see. Oh yes, infinite width network. So if you take that infinite width limit, and I showed you those 4 papers on the previous slide, what they prove to you in those papers is that essentially because of the central limit theorem, if you have an infinite number of nodes in each of those hidden layers, it says that the corrections to this equation, remember there were corrections that went like delta theta squared and higher order powers of your change in theta, those go to 0. They're infinitesimal compared to this leading order term. So in fact, this kernel represents everything you need to know about a fully connected network when you take the infinite width limit and it's fully trained, or even when it's not fully trained. It turns out that this is a real shocker to me, but this thing doesn't change. The neural tangent kernel does not change during training, and it doesn't matter what your initialization is. You stick in random weights and then go ahead and train. This neural tangent kernel doesn't depend on your initialization. That's shocking. When I first heard that, I didn't believe it. How can that be? Because it's learning, right? The network's changing its input-output relationship, but it's only changing its input-output relationship. It's only changing the input-output relationship at the output layer. If you look at the intermediate layers, the hidden layers, those things aren't changing very much. In fact, they're not changing, they're changing infinitesimally. And why is that? How does that make sense? Well, if you have an infinite number of things and they change an infinitesimal amount, and then you sum and you have nonlinearities and blah, 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 you can get the output to change in a finite way when all the intermediate layers are only having infinitesimal changes. So throughout all of learning, like why? Why do I care about this? It's because that it means that this equation tells you everything you need to know about the entire learning process for an infinite width net. And it tells you that this kernel, will not change during learning. It's only a function of your architecture, of your, whether you use ReLUs or Tanches or whatever else you use for your nonlinearities. It's only a function of how many layers you've got. We're going to take the infinite width layer, so that the width isn't going to be part of it. That's going to turn out to be, that's fixed by taking the infinite width layer. So essentially, for a fully connected network, the only question we've got is, well, which nonlinearity should we use for our activation functions, and how many layers do we have? And different choices will give you a different case. But it doesn't matter what the weights are, doesn't matter what input you're giving, this equation will always be true. So that's a really strong statement that these other authors I described for those 4 papers figured out, and we're going to exploit that. So it turns out that every kernel has an eigensystem. Kernels have they're symmetrical and they have nice properties. They're not guaranteed in all cases to be positive definite. I don't think. You can have pathological cases where you have, but we're going to focus on the cases where you can invert the matrix and we can invert the kernel to its inverse. So we're going to assume it's positive definite, and we're going to do a spectral analysis ultimately. And we sort of hinted at that with my toy model. I showed you sine waves going around the unit circle and saying, oh, look, we can think of this in terms of how well we learned different sine waves. Well, that's a good way to think about it, because it turns out a spectral analysis is how we're going to think about every problem we try to solve. So what do I have right here? I have an eigenvalue equation that's appropriate for our kernel. Our phi's are our eigenfunctions. For any given kernel, you can figure out what the eigenfunctions are. If you paid attention back in the old days in whatever class you learned that first in, and then here's your eigenvalues, right? So for any given kernel, you're going to get an eigenspectrum, right? And you're going to get a bunch of eigenvectors, and they're going to have nice properties. Well, we're going to assume this. right? That they're always positive. That's almost, I mean, that's for any case of interest, that's essentially always going to be true. So you don't have to worry, that's not too big of an assumption. And then you have this property, they're orthogonal to each other. That's guaranteed just by the structure of the function that you use to define your kernel, right? And then we're going to rewrite the function we care about in the space of eigenvectors inside this thing that's defined by, so this is our neural network, right? F hat defined in terms of these, in terms of the basis given by your eigenfunctions. Sort of a natural thing to do, right? We say, oh, let's work in that basis. And we're going to call this, we call the coefficients in front of our eigenfunctions our v hat, and we're going to call v without a hat the desired function. That's a projection of the function we want to know onto the eigenfunctions that our neural network is actually working with, right? Based on the kernel that describes its evolution during training, right? So given v, what is v hat? What do I mean by that? I mean, what is this function written in terms of these other, in terms of eigenfunctions and eigenvectors and all that stuff? Well, I'm not going to go into the details, but this long looking equation is essentially what you get when you follow your nose and you plug stuff in and keep track of your indices. And it's written in vector and matrix notation. But essentially, here's the thing we've got. Here's our neural network written as a function of the thing you want. This is the function that you're trying to learn. And all this gobbledygook is a way of, with fancy names, is a way of rewriting the kernel equation we had earlier, the kernel regression. Just we're doing it in a basis that's defined by the eigenfunctions of the kernel. So it's just pretty simple linear algebra, but it's complicated enough, and I'm not going to get into detail just to write it all out. And we're going to, and as Steve likes to say, this thing shows up a lot. It's really long. Let's give it a name. We're going to call it the learning transfer matrix, T for transfer. Okay. So now we've got a simple equation that says V times some matrix T gives us the matrix we're actually, that our network actually, sorry, shouldn't say matrix. These things are vectors, and this thing right here, this function is just a matrix times this function. That's all we're saying. And if you understand the statistics of this matrix here, and here this is expectation over some data set B of n data points. That's a first order statistic. That gives you the first order statistics of your F hat. And then you take the covariance which is a function of what data set T depends on, right? And that gives you your second order statistics. I'm only going to focus on first and second order statistics. In principle, you could go further. We haven't done that, but you could look at all the statistics of T if you want. But it turns out just looking at the first order and second order statistics tells you a lot about what's going on. So learnability, here's our new measure that we're defining. It's given as remember the ratio of those funny inner products I defined, which is, these are inner products across the entire, all possible inputs you might have seen at your network, right? And there's two kinds of learnabilities. There's learnability defined for a particular data set. And then there's the expectation over all data sets you might have trained on of a given size n. So this learnability without any qualifier, if it's a function of the function you're trying to learn, right? You're saying, how well do you learn this particular function with your network, right? But it doesn't have the D anymore in the superscript because we're averaging across all possible training sets we might have trained on of the same size, all n data point training sets. So unlike the mean squared error, learnability is bounded. It goes from 0 to 1. 0 means you're not learning anything. 1 means you're doing a perfect job of learning the function you want to learn. You're doing as good as you can. It always changes monotonically as new data points are added. Unlike the mean squared error, as I showed you empirically earlier, it's invariant to rescalings of F. It turns out that, you may not know that looking at this, but it turns out that the functional form of F hat guarantees that this is true. It's a nice property. It obeys a simple conservation law. In fact, we're going to have a no free lunch theorem that's stronger than previous no free lunch theorem as a result of the fact that if you sum the learnabilities for all possible, actually, this isn't all possible functions. It's all functions out of an orthogonal set. So if you have some orthogonal basis, which can be your orthogonal basis we defined already based on your eigenfunctions, if you ask what's the learnability across each of those dimensions, that sums to n, where n is the number of data points you trained on. That's true for a given data set, for learnabilities for a special data set, or it's true average. Well, if it's true here, it's true here, right? You average across all data sets, it's still true. That's a powerful statement. This is going to give us, this is like a conservation law. So as a physicist, that's how I usually think about it, but you can use this thing in order to make a no free lunch theorem. And both physicists and computer scientists, they may not like no free lunch theorems, but they know they're useful, right? And this thing can be accurately approximated by a very simple equation, much simpler than anything that's known for mean squared error. So it turns out it's easy to work with. So if you can express things in terms of learnability, you're in business, right? The learnability follows, I can't read mine. How do you get rid of the, so man, you know, we may be able to solve deep learning or whatever, but I'll never solve Zoom. I can't get this little bar out of here. Anyway, it follows a universal functional form, and I can't read my form, but it should look like lambda over lambda plus c. And what do it turns out, sorry, yeah, did I remember correctly?
It does, yes.
Thank God, yeah, anyway, so yeah, so so this functional form where c is a constant, it turns out empirically that, you know, Jamie and Maddie just noticed empirically that it just looked like this. They tried a bunch of different functional forms, and this one looked like a really good fit. And it turns out it's such a good fit that it allows us to make a simple, you can write down, like our theory essentially is taking advantage of those kind of observations that are hidden in under the hood of this thing that give us, there's so much structure in the problem, we can write a very simple equation. It's based on some assumptions. We're assuming an infinite wide net. We're assuming the functional form I just show you here for our learnabilities. We're assuming there's a couple averages where we take an average over all functions instead of just the eigenfunctions. We do a couple things like that. And when the dust clears, we get a simple theory. And I already showed you examples earlier that the theory worked really well. In fact, when I was showing you those interpolations and extrapolations about the data points, the generalization of my model, my toy example, those were actually not based on training a real neural network. Those were based on this theory, and it's a very good fit. So what I'm showing you now are three things. I'm asking, let's see, for three different example problems. One's a unit circle we already saw, okay? I'm also showing you an eight-dimensional hypercube, so the inputs can be, you know, it's like an 8-bit vector, right? It can have 0 or 1 for each of the elements in the vector. And then there's a 7-sphere. So what I mean by this is if you're in 8-dimensional space, Euclidean space, and then you just embed a sphere in there, right? So it's a 7 spheres, the surface is 7-dimensional. And then you grab points at equally weighted anywhere on that surface. So it's a continuous example, right? That's our input space. And then we're going to train on n data points, where n is a number of data points again, right? This is 1 data point, one data point. And then here's 4 data points. And over here is 256 data points. So same thing before, n along the horizontal axis. And we're asking, in terms of learnability, how good are we doing? And we're assessing it 3 different ways. We're doing it based on our theory. That's what these curves are, right? These smooth curves. And then we're empirically training a real neural network to do this, right? And that's what these triangles are. Pretty sure I'm getting this right. Although they're so close, it doesn't matter if I got it wrong. But actually, I shouldn't say that. There's some interesting trends and differences between the triangles and the circles. And then there's the circles, which is what the exact kernel regression methods tell us you'd get. So the curves involve some assumptions we're making, like the functional form for learnability, stuff like that we talked about. Anyway, so those are the 3 things, and they all agree because the theory works, right? And what I'm showing you is for 3 different kinds of toy problems. Now, I admit these don't involve cats and photographs. That's for the future, but we're working on that now. And I think that we're going to make good progress there because it turns out there's lots of structure in the data. It turns out if you look at what these things actually appear like in real data, I'm getting ahead of myself. Anyway, I just couldn't help myself to say that. But anyway, so here's 3 different examples. It works really well. And so I just want to demonstrate to you what I mean. Once again, I've obscured my, here we go. Oh yes, indeed, it is as I remembered. Learnability goes like lambda I over lambda I plus c, where c is some constant. And what constant is it? we don't, the theory doesn't tell us, we actually empirically tell because we have a no free lunch theorem. If you add these things up for every I, where I is for each of your, well, actually it can be for any orthogonal basis, but we actually already know what it is. We know what the eigenspectrum is, if we've gotten this far with our theory, for the basis given by the eigenfunctions of our kernel. So then if we just sum this thing up empirically, and then we get some number out, well, all right, then that, divide by, whatever, solve for C, and then just empirically find out what C has to be, what this constant has to be, so that when the sum is completed, you wind up with N, the number of data points, because we've proven that's what this thing has to sum to, right? And so to demonstrate that, here's for the 3 different examples again, right? I'm showing you as a function of now this is an N on the horizontal axis now. Now it's lambda. We're looking at different eigenvalues, right? And we're looking at essentially it's the learnability associated with each eigenvalue for each of our different modes. And it turns out that they fall on the same curve, and then I'll do sort of a physicsy thing. I'll replot it all, right, rescale it, so that all the points can, yes, they fall on the curve we told you they would fall on, right? And of course, the theory, that's what the theory gives us, because we put that into the theory. But these data points didn't have to do that, and they do because, yeah, the theory is pretty good. It's a pretty good approximation to what's going on. So there's some universal underlying structure to deep learning that we can exploit. So let me talk more about this no free lunch theorem. So David Wolpert, back in the 1990s, came up with a beautiful, he quantified something that I think must be sort of true. He proved that it's exactly true. And I'll first of all say, what am I talking about? Generalization. So suppose I'll play a game with you right now. Suppose I show you these data points. I say, how would you continue them? Well, maybe you'd guess this, and maybe in this case, you got it right, because in fact, the function on the right-hand side happens to look the way you might have guessed, right? But maybe if you extended on this side, oh, now I tricked you. I made a mirror instead of, well, actually, I guess that would agree up here. This could be a continuation of assignment, or it could be a mirror reflection. But maybe I'll do something even more bizarre over here, right? If you don't know what the function is over here and you ask, how should you generalize? Well, it's an ill-posed question in a way, right? In fact, what David Wolpert said was, if you average over all possible target functions. So the thing over here is the target function. It's the thing that you'd like to learn. And I didn't show it to you. I only gave you these as your training set. These are training data. I'm saying, hey, generalize for me. Tell me what we should get over here. Well, if you generalize, if you average over all possible things you might want to learn over here, I can't read the exact statement. Oh, here we go. All predictions have the same accuracy. That's the way to say it. So that's a profound statement. And it quantifies what we all sort of know is sort of true, right? That if you don't, if you're going to average over all possible things you're trying to learn, what is the effect of this? It says that not all networks maybe are going to be equally good at training to train to learn a certain task, right? Some might be better at some tasks than others, because you can't be good at all tasks, right? But this is such a broad statement. It's hard to put it to use in a practical way. It's tough to make a bound with this that you can use, because we're averaging over all possible target functions. That's a massive space, right? So we're going to make a tighter statement, a stronger statement. And what is that? Our statement, our theorem, right, is that, let me move this. I'm sorry, I have to fiddle with these windows. Here we go. Is that for any kernel and any complete basis of an orthogonal function. So this isn't all possible functions. It's only along the basis the orthogonal basis functions, or any orthogonal basis. This sum or this sum, right? For even if you train on a particular data set, the sum of learnabilities across every one of those directions is going to be equal to n. So that means that, unlike the last no free lunch theorem, you can't just you can't take your orthogonal system. Suppose you're in two-dimensional space. And suppose there's some bad direction that's hard to learn with your network. Oh, I'm just going to avoid it, right? I'm just going to go like this. Well, this theorem says you can't do that. If you have an orthogonal basis of any kind, you can rotate it around all you like. You're never in a situation where where the average between your learnability of this guy and this guy isn't the same thing. So in other words, you have to pay a cost in the form of not being good at learning one function if you have a network that's good, or any kernel that's good at learning another function. Yeah, this statement is true for all kernel regression, any kind of kernel regression, including fully connected deep neural nets that are wide enough to be close enough to the infinite width limit, or convolutional nets, because they have a limit. If you take the limit the right way for the width of the number of channels, it's called, doesn't matter for this talk, but anyway, for all different kinds of networks you might think of, people have proven, yeah, there's a kernel description of that's exact in the infinite width limit. And for all those cases, and for linear, and also for linear regression, this is true, right? Anyway, so what do we do with this? So here's just a proof that it's actually true, and sort of a demonstration of what I mean. So suppose you have a training set with n equals 3, training set with n equals 6. In either case, if you sum up the learnabilities, so here's for a one hidden layer ReLU network, and here's for the kernel approximation for that, and then here's for the actual learnabilities we're summing up. And what is this? This is a stacked histogram where each of these guys is the learnability for one of your 10. This is an example where capital M equaled 10. So there were 10 different possible inputs to the system. We trained it on only 3 of them in this case. And you see that, yeah, both for the real network both for the real network and for the kernel approximation, you get a really good, our no-free lunch theorem seems to be true. We're summing up to n, which is 3, is what you get. And it's also true for the 4-layer hidden network, and for different nonlinearities, tanh instead of ReLU, doesn't matter. Same thing for a bigger training set size for these networks. And you can see there's a little bit, just to prove it's real data, or real simulated data, right? Real simulations, or real training data, I should say. Yeah, the network, when you train it up, it's not exactly right, either because we didn't train it long enough, we didn't do it for infinite time, or because the approximations are a little bit wrong. The infinite width limit mattered a little tiny bit, but it's pretty good fit, right? Okay, so second order statistics. I'm going to throw some math up just to prove to you that we did some math, but I'm not going to go into it in detail. This is just looking at the covariance between those, remember that learning transfer matrix. And you get some functional form for that. And in fact, I've written it in terms, or actually Jamie wrote it in terms of learnability. So I'm writing, if I can write things in terms of learnabilities, then I've got simple formula for learnability. I can plug it in, get simple formula for this, right? You follow your nose, you do more math, you would define this thing called capital E. It's also written in terms of learnability. You can see remember this thing is your mean squared error. Anyway, you follow your nose, you do this stuff, and you plug in the beautiful functional form that Jamie and Maddie found. And then you can prove, based on those ideas, that for small eigenvalues, you'll have situations, or even actually you can get it in a few different cases, but certainly for small lambdas, this function can wind up going positive. And this is the derivative of something that the mean squared error depends on with respect to the number of data points. What I'm trying to tell you is that you can actually go up in error when you train on bigger data sets, even if you average across all possible data sets of that size. So it's not a matter of picking a really bad data training set, right? And this is just empirical evidence, or I shouldn't say empirical, I should say this is an example where we used our kernel methods. These dotted lines are based on the derivation I just sort of gave you, I gave short shrift to a second ago. The point is that when you increase n, there are cases when you can go up in terms of your error. So it's plotted on the vertical axis is your mean squared error, and then the number of data points you trained on. And sure enough, you get these cases where our theory does a perfect job of capturing what happens in the kernel description of our, it also works very well for actual networks. So here's using kernel methods without the approximation. These are simple enough models we can actually solve for the actual kernel in the kernel regression problem without making the extra assumptions beyond infinite width. And then the triangles here, if I've got my head straight. Actually, no, I think I've got it backwards. And this is reminding me, I've been saying it backwards. The circles are the actual trained networks, and the triangles are the kernel methods. I remember that because the theory does a better job of predicting the actual data, the actual trained network, for reasons we don't fully understand. Just the assumptions we make go in the opposite direction of some of the corrections that we didn't include. So it turns out that there's a happy coincidence, and the theory we worked up here does a perfect job of predicting the next point. Anyway, the point is just that error can go up with increasing data. And that's another reason we like our learnability measure. The main reason we like it, though, is we have a simple formula for it, that lambda over lambda plus c. It allows us to do so much. We can write down lots of simple formulas. Oh, and this is just showing that previous researchers had seen this. They didn't comment on it or notice it when we talked to them about it after the fact. And we've had a lot of good interactions with this group after we realized that they were a little ahead of us on thinking about kernel methods and generalizability. But anyway, they saw it as well in their, and you can see it in their paper. So this is an attempt at a very high level description of what we're trying to do with this theory that Jamie cooked up. And the idea is that our theory is it's mapped like this. We have a function we're trying to learn, and there's a network that we're faced with that has these properties. It has these eigenvalues for its kernel, and it's got these eigen functions, right? Well, so what do we do in our theory? What we do is we project the thing we want, the function we want to learn, on this basis, and we get this thing we call V, which is just, all it says is, how do you break this thing down, the function you care about, onto the basis of, so you find out what the projection is onto the basis given by the eigenfunctions of your kernel that describes your neural net, right? And then you take the we have formulas, and as I very quickly skipped past earlier, that depend on the number of points in your training set. So as a function of how many data points you're training on, right? And you've got some eigenvalues for every one of your different eigenfunctions for your kernel. You can come up with these learnabilities. And in particular, you get a learnability for every one of your learning modes, every one of the eigen directions in your kernel, right? Once you've got these two things, however you get them, whatever approximations you need to make and whatever tricks you need to do to get to this stage, once you've got this, now you can, you put them together, and now you can calculate the learnability for the entire network acting on, as a function of the function you're trying to learn. You can then talk about other things like the mean squared error and anything else you want. I just listed this one because it's an important one, but there's many other things we can do. So the basic idea is that if we want to look at more interesting cases than the ones I've shown you, the toy examples, which is what we're doing now, we're coming up with tricks that allow us to shortcut the process of going from over here to over here. We've already done that a little bit. I showed you how we did it, making those assumptions like the special form for this, the lambda over lambda plus c. But there's other tricks we're trying to find based on the statistics of natural scenes, based on the statistics of natural scenes with cats in them and things like that, we're still in the process of figuring it out. But it turns out, you'll be shocked to hear it, but there's a lot of structure in photographs of cats. There's a lot of structure in other kinds of data that people tend to use neural networks for. They don't use it on white noise, right? They use it on stuff that's structured. So that structure allows us to do tricks to figure out what these things are. Okay, next steps. Well, we're finding some things we're thinking about are ways to correct for the fact that we're using infinite with networks. I didn't show it, but in fact, if you want to see it, I can show. I have a slide in the back that shows, for a toy model anyway, you can go down to 20, a width of 20. And you're already doing a pretty good job with your infinite width approximation. And you might say, yeah, of course you are, because the central limit theorem cuts in after, like if using the central limit theorem for a bunch of independent things you're adding together and then saying, hey, it looks like it's Gaussian distributed. That works pretty well after, like in my hand, like 4 or 5, depends on what depends on how picky you are. Maybe you need 10, but for me, 4 or 5 is enough to look Gaussian. That's how impoverished my pattern recognition is, I guess. But anyway, this is all based on central limit theorem and some other ideas. So that doesn't surprise me that 20 is enough. For most examples I gave you, we were looking at 500 for our empirical networks, but you can go down a lot and it still works pretty well. So I don't think this is a huge deal. but maybe there are systematic corrections we could include that would make the theory stronger, finite training time. So all this depends on training for an infinite amount of time. The kernel assumes that we trained for an infinite amount of time. You might say, wait a minute, but you have a finite data set. Yeah, we're training with replacement. How am I doing? I guess I'm almost done here anyway, but how are we doing for time? Did I go over?
We have 5 minutes left in this session.
Wow, that never happens. Okay, let's see if I can add another half hour of fluff. Sorry, what's that?
Wait, she says 5 minutes, including questions. But we'll probably just run over.
So I'm just going to wrap it up and say that, this right here means, yeah, we'd like to understand we'd like to tell the community, here's the number of layers you want, and here's the right nonlinearities if you want to recognize cats in photos. That's what we want to do, right? No one has ever come up with a first principles theory that's going to tell you how to do that. And we think that this is the right approach to do something like that. I'm beating my chest here. We haven't done it, it's for the future, but we're trying to do that now. Those are the kind of things we want to do. And insights into linear regression, why not? Why not say something new about linear regression? I have nothing to offer you there now, but this is all the theories about kernels in general. Anyway, transfer learning, convolutional networks also obey a neural tangent kernel. It's more complicated. It turns out its spectrum is harder to understand, and no one's really gotten a good handle on it. So that's a tricky problem. But in principle, wants people to do it for convolutional nets. And that's big because that's what people use in practice more than fully connected neural networks. Anyhow, these are the people who did the work. We had useful discussions with a bunch of folks, including the ones listed here. And this was paid for by the Army and by the NSF, among others. But anyway, thanks a lot.
Great. So just to remind people in the audience to submit questions with the Zoom feature, and I will try to pass them on to Mike. And I'll start with one of the ones. Basically, I'm going to rephrase. So in terms of the basis functions, right? You gave your nice, simple, trigonometric function, example-y stuff. But I assume, well, how much have you explored the space of basis functions, orthogonal basis functions for your different examples? And does it show any pathologies for some kinds of basis functions, or does it all hold up beautifully?
Yeah, so I think the way it's going to work for real problems is you're never going to get a look at all the full eigen spectrum and the full set of functions. What matters are the most important ones. And the important ones, as I've shown you, maybe I didn't say this explicitly, but it was implicit in what I said, at least. The bigger the eigenvalue, the more important the basis function, right? So what are the neural networks you want? You want neural networks whose kernel has the most overlap, or has so that the function you're trying to learn lines up as much as possible with your biggest eigenvalue, right? That's what you want, right? And so if you understand where the big eigenfunctions are, that's great. You want to steer that toward the thing you want to learn, right? So it may not matter what's going on way off in the wings. I think so what we've done so far is, it turns out when you try to understand these things or look at, non-toy problem, or maybe you think cats and photographs, it's a toy problem, but it's not a toy problem, since it's a big, awful mess where we don't really understand the statistics of natural scenes or whatever. So that's a case where
yeah, I couldn't tell you what an eigencat looks like.
But I bet you can tell me, Steve. You've asked me this question before. So what do you think the form of the eigenspectrum will be, given that, this is a bunch of real world data and there's a bunch of things being added together? And
right. So yeah, natural scenes have those power loss things going.
Power law. What's a really interesting, so it turns out there's regularities we can exploit when we look at these things. That observation you just made takes you part of the way, to a shocking extent, but not all the way. You need to make other, you have to have other insights in order to solve that problem. But so it's really less about, in my experience so far, looking at a few toy examples and then looking at a few harder problems, it's less about pathologies that are going to trip you up. It's more about finding the regularities in natural data and the sort of problems people tend to want to solve, that will give you ideas about, how to steer your network around, how to change the nonlinearities, and how to change the number of layers, or whatever it is you got, whatever handles you've got on your network. so that you get you get the biggest eigenvalue directions lining up with the things you might want to learn, with the function you're trying to learn. So I don't have a good answer. So I changed your question because I don't have a good answer for pathologies, but that seems like the way what we're spending our time thinking about mostly.
So you're a learnability guy, right? Who looks like a regression slope, right? But he's a funny slope because he's the slope from truth to approximation, not the slope from approximation to truth.
Are you talking about these kind of curves?
The F, the bracket F ratio, right? So I think you have on the top, you have the two Fs, right? Which is the truth.
Yeah, just the definition for.
Yeah, you have the F and the F hat, right?
Yeah.
So that's literally like the regression slope in some sense, right? From the truth to the approximation. And so, first of all,
I
think that's bounded by 1, right?
Yeah. I haven't proven that to you.
Because if F hat is 2F, that's 2.
Of all the people I know, you might be somebody who'd look at this equation and say, oh, of course it's bounded by 1. But I can't look at this thing and tell you it's bounded by 1. And in fact, I don't think Jamie or Maddie would be able to either. It just turns out
the property of how you generated F hat, right? Like if they make F hat 2F, that's 2. Right?
Yeah. So
the generation process for F hat has to preclude that happening somehow.
Absolutely. And reviewers complained about this. Hey, what a scam, like a swindle. But it turns out that if you read our appendix carefully, or I forget where we put it, but it turns out that if F hat is defined according to the equations I've got on other pages, like this right here is an equation that relates V hat is just F hat written in a certain basis.
Probably related to the positivity of your eigenvalues, actually.
Yeah, I think that's right. But it's more, but probably more than that. It has to do with the structure of with the structure of kernel regression. And it turns out that yes, if you put all those things in, you can show that this guy can't be bigger than 1 and it can't be smaller than 0. But you're right. If you have some non-kernel way of relating F and F hat, a non-regression way, then you can get your learnability it can be all kinds of crazy things.
It's also intuitively, it's a funny thing, like I said, because that's the slope from truth to, approximate fit, right? And you think you want the slope from approximate to truth, right? Like it seems like F hat should be on the bottom, right?
So it's symmetrical with respect to exchange left and right, but you're saying denominator, you want to see F hats on the bottom.
Well, that would be the intuitively, that would seem like the natural thing, right? Because usually what you ask is I make some predictions and what's the slope from my predictions to the truth, not what's the slope from the truth to my prediction. Right? So
I have to say that both in preparing for this particular presentation and every time I've gone through this stuff in detail, or I get my sign wrong all the time about which way we should be putting the hats and the non-hats all the time. And maybe it's because of the intuition you just described, but I wish I had a pithy answer for you, like, oh, it has to be this way because of X, Y, Z. My stupid answer is that if you just do the algebra, this is what you get.
It's just an interesting result, but
I don't have I'm sure there's an intuitive answer for what you're asking, and I don't have it when it's ready. And I'll think about that, or I'll ask Jamie, and maybe he's got it. But I do remember though having the last question you asked about why should this be bounded. So one question we could ask is, well, would this still be bound? I think that's one. Like, would it have the properties I want if I put hats on the bottom? But again, I'm not clever enough to look at this and see that would be the case.
It'd be interesting to see if you could study the object with hats on the bottom and if it had any useful intuition to provide. But
and the answer is for sure there's intuition there, but I don't have a ready, simple thing to tell you.
Like any good physicist, I cannot remember all these different things statisticians do with their regressions, with ridges and lassos. But I believe, right, that this one over lambda plus c form thing that you're finding, right? Like one of the many and most popular, right, is to just bump up all your eigenvalues by
I think that is ridge regression.
That's equivalent to adding something to the diagonal, right? And if you think about that in Gaussian process land, right, that would be equivalent to saying roughly every data point you've observed has its own idiosyncratic noise, right? And
Yeah,
then if I give it the same idiosyncratic noise,
I think
that
that's
adds the diagonal. And then your 1 over lambda c is just the eigenvalue of the regularized inverse, right?
so. I'm everything you said sounds right to me. I'd have to review to get that to say it accurate to be a reliable source of truth. I have to actually go remind myself the details. But yeah, what we're doing here does have a lot of connections to ridge regression, or what we're discovering, I should say. Well, no, I shouldn't say doing, because in fact, that formula, right, with the lambda over lambda plus c, we've intuited that, right? That's not exactly right. Even for the infinite width limit, and even for other assumptions we made before we got there.
Yeah.
That's an ansatz, if you like, that Jamie and Maddie made. So in a way, it's so it could be that what we're discovering, right, is, oh, here's a more principled way maybe to think about why ridge regression is a good idea with these kind of models, or why is it that seems to do something useful? Oh, it's because when you look at the eigenspectrum and the eigen of the kernel, blah blah blah, it turns out that functional form takes you very far to the final. You only have to add a little bit of correction to that, know.
So you did your ridge regression on ansatz works pretty well, right? And then you made your beautiful rescaled curve, and then you didn't tell us what the shape of the beautiful rescaled curve was.
Oh,
is it a universal shape? Is it like presumably?
I think it's just that same function, isn't it?
One more page, I think, right?
So what am I plotting? I'm plotting this versus that.
You made all those data collapse.
Oh, darn it. Yeah, you're right. So my dependent variable is lambda, my independent variable lambda. So yeah, what is this function? Oh, can I do algebra in front of people? I don't think I can. If I multiply,
you have to guess an error function, right? Because you did a whole bunch of activation functions and that didn't matter. And you've done the whole thing relies on this Gaussian limit. So you have to guess that it's an error function.
I think the oh, you're saying that it's going to depend on, I think the answer is just get rid of the i's here, solve for lambda, and that's what this curve is, right? So God, can I do it in my head? Lambda times L plus L times C. So I got, I think I'm going to get a sigmoid. This is what I'm going to get.
Oh, like a Lorentz sigmoid kind of thing.
But
all right. Well,
go ahead and plug it in, and you'll get one of the different forms for a sigmoid, and that's what this curve is.
Okay, so you're saying that the shape of the curve was already implied, and you didn't bother to remark on it because
I'm sorry, I should have
trivial.
Too trivial. Yes.
As an exercise to the reader.
What you said a minute ago, like any good physicist, I forget the details of the, but yeah, it's just this inverted, and then you get a sigmoidal shape. And it's true for all different, it doesn't matter which of these models you look at, these aren't different models, I guess. They're different types of data in the space of, it's all, and then we've got different models. Actually, these are all the same model. They're all the same network. It's just that we're choosing different possible inputs they might experience. And anyway, there you have it.
All right. I think that question was isomorphic to something we've already talked about. So I'm going to call us done with questions, and thank you for your talk.
Yeah, thanks a lot, Steve. It's a lot of fun.
Thank you, Mike. Remember, come skiing. It's going to snow here one of these days.
Yeah, actually, I'll talk to you about that. All right.
Offline. Bye.
Thanks a lot.